Hello grade 12s and welcome to today's lesson. In this lesson we are going to explore infinite geometric series. Today we join Donovan, who is going to help us identify infinite geometric series and investigate a formula to solve questions involving this series.
In our previous lesson, we explored a series called a geometric series. We said that a geometric sequence is an ordered list of terms with the characteristic that terms of the sequence are all a fixed multiple of the term before, and that we call this multiple the common ratio. One example of a geometric sequence that we studied looked as follows. We worked out that to get from 4 to -2, we needed to multiply by -1/2. Similarly, we got from -2 to 1 by multiplying by -1/2. And in the same way, we determined all of the terms in the sequence by multiplying each term by -1/2. We called -1/2 the common ratio of the series. We also established that the general term of a geometric sequence or of a geometric series is given by the formula t subscript n, the nth term, equals the first term a multiplied by r to the power of n minus 1, where r is the common ratio. Then we looked at the sum of n terms in a geometric sequence. We found that this sum is given by the formula s subscript n, the sum of n terms, equals a, the first term, multiplied by r to the power of n minus 1, all divided by r minus 1. We can also write this as s subscript n equals a multiplied by 1 minus r to the power of n, all divided by 1 minus r. The two forms have the same value. It is just useful to use the second one when r is smaller than 1, and the first one when r is bigger than 1. That way we avoid negative numbers in the denominator. Although we may not have been that explicit about it in our previous lesson, you should realize that this formula assumes that r is not equal to 1. This is because if it were, we would get a fraction with a denominator of 0, which we know is undefined. Finally, we noted that all information for a geometric series can be summarized like this using sigma notation. In this lesson, I would like to look at a special group of geometric series. This collection of geometric sequences have a very special property. No matter how many terms you add together, their sum will not exceed a certain amount. I'm sure that this statement doesn't make complete sense right now, but hopefully by the end of this lesson, you'll be able to grasp the idea. The best way for me to explain this concept is to introduce you to a geometric series that fits into this special group. I'm going to do this by telling you another story. Zeno was a Greek philosopher who lived more than 2,500 years ago. He was famous for having posed a number of problems. The most famous was that of Achilles and the tortoise. The story goes that Achilles, a very fast and well-respected athlete, was challenged to a race by a tortoise. Achilles accepted the challenge, but being such a great athlete and wanting to show his sportsmanship, suggested that the tortoise be given a head start. He suggested that the tortoise start 100 meters ahead of him. The tortoise accepted the offer and smiled to himself. Achilles and the tortoise shook hands, and Achilles walked back 100 meters to his starting position. The starter's gun was fired, and Achilles and the tortoise both started running. The tortoise had smiled when shaking hands. He already knew that Achilles could never catch him. Because, as Zeno the philosopher had explained, for Achilles to catch the tortoise, he would first have to reach the point where the tortoise was at the start of the race. By the time that Achilles reached this point, the tortoise would definitely have moved some distance already. And for Achilles to catch the tortoise, he would next have to reach the point where the tortoise was when Achilles reached the point from which the tortoise had started. By the time that Achilles reached the next point, the tortoise would definitely have moved some distance again. And so the problem continued. Arguing in this way, Zeno claimed that it was not possible for Achilles to ever catch the tortoise.
That was a really interesting story. Did that guy Zeno really believe that?
Why do you ask?
Well, let's just think about it. Common sense tells us that Achilles will catch the tortoise. I mean, if you took this line of arguing seriously, then nobody who's at the back of the field could catch anybody in front of them. And we've seen people come from behind to win races all the time.
Which brings me to the word that captures just what you have been saying. The word is paradox. A paradox is a statement that seems to contradict common sense and yet at the same time to hold some truth. Our common sense tells us that Zeno was wrong. But is there a flaw? An obvious error in his argument?
Well, I don't see it yet, but give me some time, I'll find the error.
The story of Achilles and the tortoise is known today as one of Zeno's paradoxes. I don't want to examine this any further now, but I would like to use it as inspiration for today's lesson.
What's that for?
Well, I'm going to use this piece of string to illustrate how we could look at Zeno's problem or paradox in a different way. Let's pretend that this string represents the distance that Achilles starts behind the tortoise.
Okay, and then what?
For Achilles to catch the tortoise, he would first have to cover this distance. Agreed?
Sure.
Now this is where it gets interesting, because to cover the whole distance, he would first have to cover half the distance. So let's split this piece of string in half. Let us say that this half here is the first half of the distance covered between where Achilles started and where the tortoise started. Now, what does this other piece of string represent?
I guess it represents the distance that Achilles must still travel to reach the point from which the tortoise started.
That's absolutely correct. Now we have the same situation again. For Achilles to reach my end of the string, he must first reach halfway. Now, what do these two pieces of string represent?
I suppose that the first represents the distance he has just covered, and the second piece you are holding represents the distance still to be covered.
I see that you're starting to get into the spirit of this. Now let me ask you, what is the length of this piece that I'm holding in terms of the original distance? In other words, the original piece of string.
Well, how long was the string to begin with?
We aren't going to worry about the measurement right now. I just want you to think about the distance to be covered.
Okay. Well, in that case, we started by dividing the string into two equal parts. So I suppose that each of those pieces represented one half of the distance.
Keep going.
And I suppose that the last piece is one half of one half, which is 1/4. And the other piece is also 1/4.
So what you're saying is that so far we have broken the whole string up into one half of the original string, 1/4 of the original string, and we still have another quarter left, which is the distance that Achilles still needs to cover. Let's keep going in the same way. How long is this piece now that I have cut it in half again?
That's a half of the 1/4, which is 1/8 covered and the same distance to go.
Great. Let's keep going a little longer.
So that piece is 1/2 of 1/8, which is another 1/16 covered and still the same distance to go. Then the new piece is 1/2 of 1/16, which is another 1/32 covered and 1/32 to go.
This piece of string is getting pretty short now.
Well, Achilles is nearly there.
Are you sure?
Of course.
Okay, we'll keep going.
Now that piece is 1/2 of 1/32, which is another 1/64 covered and still the same distance to go. And when we repeat that, then that piece is 1/2 of 1/64, which is another 128th covered and still 128th to go.
Hold on. This piece of string is getting a bit too small for me to cut. Let's move on to a different approach. We can continue this pattern by using a diagram of what we've been doing. I have a diagram already started here. Think of this line as the distance to be covered. The first thing we did was to cover half the distance, which left us with this distance still to cover. Next, we covered half of the remaining distance, which left us with this distance still to cover, and so on. And by this stage here, the distance that's left is pretty short. But I wonder if you can see something happening.
Well, I'm not sure I know what you mean.
Well, have you noticed that the distance remaining could never be 0?
Never be 0? It gets pretty close though, doesn't it? I mean, like you said, it's getting harder to cut it in half because it's so short.
Sure, it's getting hard to do the actual cutting. But if you think about the numbers only, you should see that although they are getting smaller and smaller and even smaller, there will always be a very small piece left over. In other words, we will keep getting smaller and smaller fractions.
I suppose so.
Now, if I take all these fractions and write them all like this, can you see that all of these fractions added together will never quite get to 1? We can get really close to 1 by adding more and more of the fractions, but added together, the answer will always be a fraction, and therefore less than 1. What I also want you to notice is that this is one of the series that we have been working with. Can you tell me what type of series this is?
Isn't it a geometric series? Because we get from one term to the next by multiplying by a fixed amount, and in this case, 1/2.
Quite right. This is a geometric series, but it is a geometric series with a special property. In the special type of geometric series, we can add as many terms of the series together as we want, and the sum will never exceed a given amount. In this case, the sum will never exceed 1. Alright, let me summarize what we have seen here in general terms. Given the sum formula for a geometric series, in those cases where r is less than 1, or more accurately, when r is between -1 and 1, and n is very large, which we denote by saying as n tends to infinity, then the sum approaches a divided by 1 minus r, and we say the sum to infinity equals a over 1 minus r. Magava, I wonder if you would mind testing this formula for our example.
Okay. An infinite number of these terms can be determined by a over 1 minus r. In our case, a is the first term of the series, which is 1/2. And r is also 1/2, which gives me 1/2 over 1 minus 1/2, which is the same as 1/2 over 1/2, which is 1, just as we predicted.
I think it is important to stress here that this will only be true if the common ratio is greater than -1 and less than 1. Just to prove the point, let's look at how the sum of a geometric series behaves when r is not between 1 and -1. Consider the following series. It is written in sigma notation. The sum of all the terms, 3 times -2 to the power I minus 1 from I equals 1 to I equals n is 3 times 1 minus -2 to the power n divided by 1 minus -2. I would like you to please use the formula to calculate the sum of the 3 terms, 4 terms, and 20 terms.
Right, I'm done. At least I think I have the right answers. The sum of 3 terms is 9. The sum of 4 terms jumps to -15. And the sum of 20 terms jumps way down to -1,048,575. And I'm guessing the sum of 21 terms would be a huge positive number. Am I right?
Indeed you are. The sum jumps to more than 2 million. And as n gets larger and larger, the sum jumps from a very large negative number to an even larger positive number. In cases like these, the series sum does not converge on a particular number, and the sum to infinity doesn't exist.
Well. That really is pretty impressive. Provided r is between -1 and 1, we have a geometric series for which we can take any number of terms and add them together and not exceed a given total.
Quite an interesting idea, hey?
Yeah, but it leaves me wondering about that guy in the tortoise. He does catch the tortoise, right?
Sure he does.
Thank you for joining us, grade 12s. Be sure to try the task video at the end of this series where you can practice questions involving infinite geometric series formula. You'll also be able to learn more about infinite geometric series on our website, that is www.mindset.co.za/learn. Goodbye.
Equals a, the first term, multiplied by r to the power of n minus 1, all divided by r minus 1. We can also write this as s subscript n equals a multiplied by 1 minus r to the power of n, all divided by 1 minus r. The two forms have a geometric series. We said that a geometric sequence is an ordered list of terms with the characteristic that terms of the sequence are all a fixed multiple of the term before, and that we call this multiple the common ratio. One example of a geometric sequence that we studied looked as follows. We worked out that to get from 4 to -2, we needed to multiply by -1/2. Similarly, we got from -2 to 1 by multiplying by -1/2. And in the same way, we determined all of the terms in the sequence by multiplying each term by -1/2. We called -1/2 the common ratio of the series. We also established that the general term of a geometric sequence or of a geometric series is given by the formula t subscript n, the nth term, equals the first term a multiplied by r to the power of n minus 1, where r is the common ratio. Then we looked at the sum of n terms in a geometric sequence. We found that this sum is given by the formula s subscript n, the sum of n terms,
Hello grade 12s and welcome to today's lesson. In this lesson, we are going to explore infinite geometric series. Today, we join Donovan, who is going to help us identify infinite geometric series and investigate a formula to solve questions involving this series.
In our previous lesson, we explored a series called